how's it going? So today we are solving the problem called merge intervals. In this problem, you're given a few intervals right here, and your job is basically to merge them if there's an overlap between them. So as you can see here, 2 comma 6 and 1 comma 3 is something that we could potentially merge. 8 comma 10 and 15 comma 18 don't really overlap with any other, so we don't really have a choice there to merge them with anything. And so if we merge these two items over here, this is what the final output should look like. If we merge 1 comma 3 and 2 comma 6, and we try to extend it as much as possible, it would come out to be 1 comma 6. This would just be 8 comma 10, and this would be 15 comma 18. And so as you can see, in order to get the output, we have to rely on overlaps. And visually speaking, if we want to see how the overlaps work, I can graph this out. That would basically be like a better representation of what you can see in terms of overlap. So if we put these items in our graph, we'll basically get something like this, where this would be 2 comma 6, and then 1 comma 3 would be here, and then this would be 8 comma 10, and then we'll have like 15 comma 18 here. And so as you can see, that what this does, it's kind of creating like 3 separate groups. This being one group, this being another group, and this being another group. And the way that this becomes one group is because of this overlap. And since there is some space here, this becomes like its own second group. And this is where we get the final answer. So this 1 comma 3 and 2 comma 6 becomes this 1 comma 6. This 8 comma 10 becomes this thing, and this becomes our third interval in their output. So this is how you can basically get these intervals. It doesn't matter what order the output is in, but this is what the intervals should look like in your final output. So let's look at how you can actually get to these intervals. So I'll just pull this down here. So what you kind of have is this intervals first of all, and you need to kind of go through all these intervals one time to just see if they are see what the intervals are, and also see if they overlap with any other interval in your interval set. So what that would require is for you to have like a for loop. So we will have like a for loop here that would kind of go through all of them. And when we're traversing them, we'll kind of go over each one of them one by one. So let's think that we're going over the first interval here. Now what we'll need to do is compare this with all other items and see if there is an overlap with this item and any other item in the list. So what that would require you to do is have like a second pointer that would kind of see if there's an overlap. And in this case, what it will do is go over this one, and this one. But when it's on this one, it'll see that, oh, there's an overlap. What that would require for it to do is compare these two intervals and try to maximize the time frame as much as possible. And once done that, it would update itself to 1 comma 6. So this would become 1 comma 6. And since we found an overlap, this is basically not our final interval. But let's say when we are on a case like this, 1 comma 3 doesn't have any overlaps with the remaining of these items. So that means that 1 comma 6 would not have any overlaps with the final any other items. So 1 comma 6 would be something that's going to be part of our final output. And it's going to be the same case with 8 comma 10 and 15 comma 10. They don't overlap with any other items, so they're a part of the final output. So once we kind of have this first for loop, we use a second pointer that would go through every single item after this current one to check if there's an overlap with the current one. So what that would require to do is set up a second for loop inside of this for loop. That would do and that would basically have the logic to compare the time frames. And speaking of in terms of complexity, this first for loop here would basically take big O of n times time complexity, and this one would also take big O of n time complexity. And so if I put them together, it would look something like big O of n squared complexity for this method. Now, as you already know, we want to strive for better than big O of n squared. And so this would be something like a greedy method. And we can look onto improving on this method. So what do you think here that we can do differently? You need to basically identify a few of the important points here that can be potentially improved on this algorithm. So let me take this down and we can see what we can improve on in this method. So there's essentially two ways that you can use to improve your runtime complexity. One could be like a data structure. You can, in any method, you can maybe use a data structure that can reduce your time complexity. Obviously, the giveaway is you using more space complexity. Another thing that you can do is use an algorithm that you can use prior to your method or inside of your method that runs in a lower time complexity than what you're currently using. So what we can do is, in this case that we identified, is that when we're comparing the time interval to another intervals, that we found that we're actually going over each interval n squared times. And so the comparing part is basically what we can optimize on. And in order to do better with that, we can actually sort the given input. And what that would allow us to do is we would only have to compare the interval before the current interval. Let me show you how that works. So if we sort this input from just taking the first item as the key, it would look something like this. This would be swapped. And so once that is swapped, we would need to, when we are on 2,6, we would only need to check the item before it. And the way that would work is that this 2 would be compared with this 3. And if the 2 is actually lower than the 3, that we know for sure that we found an overlap. And we can keep on doing this for the rest of the intervals. And what that would lead us to is that we are only comparing since we're only comparing like the previous item, we don't have to do like an n squared loop over here. So we only have like this one for loop. And inside of this for loop, there would be some compare logic. And above this for loop, we're gonna have this sorting the input. And so now, since we're only comparing to this item before this, we don't have a nested for loop. So we know for sure that we don't have like an n squared complexity. So speaking of complexity, our sort input would be a big O of n log n. And our for loop would be just big O of n. And so our final complexity would be something like big O of n log n plus big O of n. that would basically equal to the entire complexity being big O of n log n for the algorithm. So as you can see, we came down from n squared to big O of n log n. Now let's go ahead and see how this would look like in code. So this is our basic implementation of the merge intervals problem. You're given a vector of vector, which is going to be the intervals given to you, and then you're going to return the vector of vector, which is going to be the merged intervals. In here, first we'll look at some edge cases. There's only one edge case is where the given interval vector is probably empty, or there's less than one interval, in which case you cannot merge them, and so you just return the given input. After that, we'll look at the sorting part of it. For this, you can just use the standard C++ sorting library, and if you're using a different language like Python, you can also use a standard sorting library for that. And in here, you just use intervals.begin and interval.end as two parameters, and that would sort the input as to however you want. After that, what we'll do is look at the merging part of this. And for the merging part, we'll need to have a vector here, which would be like a result vector. And this is where we would input all the outputs, and at the end, we'll just return that as part of the function. And so instead of this, what we'll first do is input one of the first intervals, so that when we're looping through the intervals, we have something to compare it with. So we'll just push back the first interval. And so our for loop would start from I equals 1, not the I equals 0, and it would go until the end of the intervals. And inside of this, we'll have a if statement that would check if there's an overlap with our current intervals against the last interval in our results vector. And the way it checks is it looks at the starting of our current interval and compares it against the ending of the result, the last vector, last time frame in the result. So if the current one is overlapping with the result, then it will need to get the maximized time frame and update the result vector or the result time frame. But if there's no overlap with the result time frame, that we'll just need to push back the current interval. So let's first look at the pushback. That should just be this one line. It will just push back the current interval and move on. But if not, then what we need to check if our current interval is actually maximizing the last time frame in the result. And the way we would check is we would compare the ending of both time frames, and we would make sure that our current one is actually larger than the last time frame in the results. Because in some cases, what it could be is just, it could be an inclusive time frame. It could be just a part of the time frame that we already have, and we don't want to shorten the time frame. So we need to check if we're actually maximizing it. And so if we know that we're maximizing, then we'll just update the time frame in the result. And there you go. This is basically the implementation for the C++ code, which would merge all of our intervals and output the results. And this is a quick implementation in Python. If you're curious, it follows all the same process. There's a sorting one, there's an edge case, and it's also following the same for loop. This is just a same implementation in a different language.